Hi, everyone. Welcome and thank you for joining us at the Introduction to Power Quality Effects on the Network and Mitigation Strategies webinar today. I'm your host, Carmela Pablo. Before we begin, I just want to go through some housekeeping with you. You will be put on mute during the presentation to reduce background noise and disruptions. Should you wish to ask a question, please type the question in the chat box. We will save all of the questions at the end. Now, I'd like to introduce our guest speaker for today, one of NHP's electrical engineer application engineer, Ravi Panneer. Ravi has been with NHP for 7 years, specializing in low voltage power distribution, circuit protection, energy management, and power quality products and technology. Ravi holds a bachelor's degree in electrical engineering. His experience in power quality comes from being involved with various stakeholders, providing power quality audits and reports, and subsequent implementation of mitigation strategies from initial design phase to installation and commission. So now, without further ado, I will pass you over to Ravi.
Thank you, Carmela. Hello, everyone, and thanks for logging into the webinar. Today's topic, as Carmela stated, is Introduction to Power Quality Effects on the Network and Mitigation Strategies. So in this webinar, we will cover off on power quality, what it means, the differences between displacement and distortion power factor and why that is important, technologies available today to rectify bad power quality, some examples to see what the situations are in real life and how to identify power quality problems within a network. So the deal with power quality. Good power quality is the ability to deliver a clean and stable power supply, essentially a pure noise-free sinusoidal wave with voltage and current and phase free of any disruptions. Everybody has most likely seen the different analogies used before for power quality, such as the beer ones or the chips analogy. Just to summarize, electrical power is composed of real power, reactive power, and apparent power. Real power, measured in watts or kilowatts, is the power that does the work required by applications. It's the power which usually performs the work, i.e. turning a motor shaft. Reactive power, measured in volt amperes, reactive, or var or kvar, kilovar. So inductive loads and capacitive loads will absorb energy during part of the AC cycle, which is then stored in the device's magnetic or electric field. This energy then returns to the source during the rest of the cycle. Capacitors are set to supply reactive energy. Inductors are set to consume reactive energy. In reality, the energy is just moving back and forth between device and source. But keep in mind, inductive loads like motors and transformers require reactive power to create magnetic fields to allow the work to be performed. Reactive power is also typically added by utilities as excess charges. And then we have apparent power, also called total power. Simply is a combination of active and reactive power. Apparent power is measured in volt amperes, VA or kVA. There are commonly three main power quality issues. Power factor. A poor power factor is caused by phase angle difference between the current and voltage waveforms of an AC system. Then there is harmonics, which are multiples of the fundamental frequency of 50 Hz affecting the supply, which results in heavily distorted waveforms. Then we have network imbalance. Differing line voltages between the phases predominantly caused by unbalanced load and single phase and phase-to-phase connections. So let's look at power factor. Power factor is a measure of the efficiency of an electrical system. It is a ratio of true or actual power to the apparent power in an AC system, also referred to as total power factor. Total power factor consists of two terms: displacement power factor and distortion power factor, which we will look at shortly. Poor power factor can result in higher running costs due to inefficiencies, higher maintenance, increased equipment failures, or reduced life expectancy, which translates to more downtime or lost productivity on a site. Then there are potential penalties from power utilities for power quality issues, which are deemed outside of regulations. You can typically find these excess charges or on-demand charges in your utility bill, and it is based at the highest demand over the period. So let's continue with the power factor. So power factor is a dimensionless number ranging from 1 to -1. Let's look at the voltage and current waveforms below to see what this means. In the first one is a waveform of supplied voltage to an AC circuit and the current through an inductive load. The current encounters the 0 point of the time axis some phase after the voltage. This is referred to as lagging power factor. And in the figure next to it, the current encounters the 0 point of the time axis some phase earlier than that of the voltage. This is referred to as leading power factor and is due to capacitive loads, some type of electric motors, capacitors, and the like. Displacement power factor caused by inductive loads, such as three-phase induction motors, is the most common and referred to type of power factor. To put it simply, it is a phase angle difference between the voltage and current. The greater the angle of the differences, the less efficient the site is at consuming power. Displacement power factor accounts for the relationship between current and voltage at the fundamental frequency at 50 Hertz. Note, for a site where harmonics are present, displacement power factor may represent a small percentage of the overall true power factor. If there are no harmonics present, then displacement power factor would be equal to the total power factor. So also note that commonly used equipment used to compensate for power factor only improve lagging power factor. So harmonics, as stated earlier, are multiples of the voltage or current waveforms in relation to the fundamental frequency of 50 Hertz. Harmonics are caused by nonlinear loads, which draw non-sinusoidal current, loads like VSDs, LED lighting, switch mode power supplies. We can see the different harmonic current waveforms of various orders. The fundamental at 50 Hertz, or the first harmonic. Then we have the third harmonic, then the fifth harmonic current shown. And then the sum of the total harmonic current, which can be seen as a heavily distorted waveform, which is what harmonic mitigation corrects to produce a smooth and healthy waveform, as harmonic distortion can cause serious issues at an electrical installation. Issues such as overheating of electrical supplies, conductor losses, poor power factor, large load currents in the neutral wires of a three-phase system. We can have malfunctioning of equipment such as computers, motor drives, and other sensitive electrical and electronic equipment. It can cause tripping of protective devices. It can cause voltage distortion on neighboring power supplies. So what happens when some of the current within a system is not at the fundamental frequency? Well, when harmonics are present caused by nonlinear loads, such as VSDs, this will impact the distortion power factor. Distortion power factor is caused by the presence of harmonics in the current waveform. It is represented by the ratio between the current at the fundamental frequency and the total current, including the harmonic current. Please note that most commonly installed equipment for power factor correction have no desired effects on harmonic mitigation. In some cases, distortion power factor needs to be addressed before displacement power factor is corrected. Now let's look at some commonly used mitigation technologies in the industry. The most well-known solution in the industry is through the use of capacitor banks. They're the most common solution used for correction of displacement power factor. They're designed to provide capacitive steps of various ratings, typically though at 12.5 or 25 and 50 kVAR banks or steps. Applications include buildings and factories with predictable loads. That's key there. The capacitors in this system are switched in and out using contactors. In terms of advantages, capacitor banks have lower upfront costs compared to other mitigation technologies. They produce less thermal heat or watts loss. They're fairly easy to install and also to service. Maintenance can be considered to be low, but should not be neglected as the capacitors themselves are very sensitive to heat and are quite temperamental and prone to failure. So it is good to check on them regularly or as per manufacturer's recommendations to make sure they have not failed. And if they have failed, then the PFC system will not be effective. Things to consider when using a PFC system based on capacitors. Capacitors will only correct for lagging power factor. So if leading power factor in your site or system is of concern, then they will not be effective. The response time to hit the target power factor is a lot slower. In some cases, it might take minutes to actually reach the right level. And the steps are also granular depending on the step size. For example, if your system is set to 50 kVAR steps and you only require 20 kVAR or 30 kVAR compensation, you are either under or overcompensating. For most capacitor banks, the connecting system also must be typically under 20% of harmonic current, or THDI, as it is shown, as we mentioned earlier. So it's also good practice to check with the respective manufacturer's recommendation on what their PFC equipment's harmonic limits or distortion limits are. So site harmonics must be taken into consideration. Now let's look at a more advanced technology, static Var generators, or SVGs. As the name states, it generates reactive compensation based on inverter technology. It can respond dynamically, that's the key word there, to power factor requirements. SVGs can correct for both lagging and leading power factor. They have a very quick response time, up to 20 milliseconds, a long service life, typically about 10 years plus. Internal components also have a very long service life. There are no moving parts other than cooling fans and any other materials part of the enclosure assembly. SVGs are also not typically impacted by high harmonics. General applications are for low voltage networks where the load is not consistent or predictable, such as sawmills, fast switching of motors, welding equipment, or injection molding equipment, and where you have commercial buildings where there are many different and unbalanced loads. The major advantages of an SVG is they can correct power factor to 0.99 consistently for both lagging and leading power factor. This is one of the reasons why you can use SVG systems and their technology with the generators on site. They support dynamic stepless correction. So no steps like you have with the capacitor-based systems. So the compensation is just right. Very quick response times, as mentioned, 20 milliseconds. They have load balancing capabilities and immunity from site harmonics as stated up to 40%, but please check with the manufacturer's recommendation or product specification. 4-wire models can correct non-balanced networks, which is an often overlooked feature. Very low maintenance requirements, requiring general clean every few months. Now let's look at active harmonic filters, also known as AHF or APFs, that can correct for both power factor as displacement and harmonics, so displacement and distortion power factor. So APFs inject adaptive current that matches the harmonic's magnitude, but at opposite phase angles, restoring the waveform to a smooth sine wave, which we looked at in the harmonic section where we had the distorted waveform. By mitigating harmonics, the APF is improving the distortion power factor. APF systems can also correct for both leading or lagging displacement power factor. The internal structure of the APF is identical to the SVG, but the inverter components or IGBTs do have a higher switching frequency. Some of the advantages are quick response times, as stated earlier, similar to the VST, SVG, 20 milliseconds, load balancing capabilities with 4-wire models, and low maintenance requirements. However, you will need to consider higher initial investments, as this technology is typically more expensive than the previous technologies mentioned. But keep in mind that the APF can provide both displacement and distortion power factor correction and load balancing, essentially an all-in-one device. Now, let's look at some examples that has been experienced. A customer had engaged a supplier authority due to issues with the transformer after major upgrades to site. Claims of improper installation and faulty equipment were made by both sides. After completing a comprehensive investigation and on-site analysis, it was found that through a power quality audit that after the site had upgraded several pumps and installed large VSDs, there was a high amount of harmonic distortion present. And since there was no harmonic filtering on site, it was this harmonic distortion that had led to the transformer overheating on the LV terminals and causing numerable issues on site. So once the power quality analysis confirmed the issues of harmonics, we were able to implement our active harmonic filtering, our active power filter, APFs, to resolve the issue. So this is one of many cases where harmonic distortion within an electrical system can have profound consequences. So it must be kept in mind. So another example, this time at our manufacturing and warehouse facility in Laverton. We conducted power quality analysis after observing power quality issues. Through the analysis, we observed displacement power factor on site. Displacement power factor issues on site, which comes from heating, cooling, and ventilation system. This peaks throughout the day between 6 a.m. and 5 p.m., where at times the power factor fluctuates and would drop to 0.8. Once we implemented the SVG, the power factor became very consistent, sitting at about 0.98 with no under or over compensation. The SVG effectively increased the efficiency of the entire site. This was installed in August 2018 and is still running to this day. Note that an active harmonic filter could have been used in this case to achieve the same result. However, it would not have been sound economic decision to do so, as we were compensating for displacement power factor and not distortion power factor. A capacitor-based PFC system could also have been installed at this particular site, but after discussions, it was determined that it was far more effective to use a SVG, as it would require less overall maintenance through its life cycle, and there was no need to use capacitors and constantly replacing them. The next example, we look at a mixed-use commercial building. So after the customer complained of poor power factor and asked to purchase a capacitor-based power factor correction system. But initial discussions with us led to us advising to conduct a power quality audit to determine the nature of any higher issues or the nature of the issue. We observed that harmonic currents were quite high, approximately 30%. So THDI was 30% on average during the recorded period. But when we checked the displacement power factor, it was close to unity. And we checked that with the true power factor, which showed it was significantly worse than the displacement power factor. So distortion power factor was the issue, and that can be verified by comparing the displacement power factor with the true power factor and also the total harmonic current. So we verified and established the presence of harmonic distortion in the system. So we were then able to implement an APF at the right level. And after implementation, the site now sits with a harmonic current of approximately 4% THDI, leading to an overall healthier installation with the reduction in phase currents and even neutral currents and a better overall power factor. Note that an SVG would not have been effective at all in this situation, as the issue was with harmonic distortion or harmonic currents, and rectifying or compensating for displacement power factor would not have helped at all. So it is always advisable to conduct a power quality audit to thoroughly analyze the current, voltage, and power and harmonic distortion to ensure the right technologies are being implemented and get the most effective results on a site. So looking through a site, some common and simple methods that can give a general idea of on-site power quality. So to start off with, it is best practice to check the voltage and to see whether it is within the SIR limits, state and territory ribbon, that is service and installation rules. It is also good practice to check the power factor through on-site equipment or metering. It is best to check during peak load, so to ignore or remove any unnecessary data. As during peak load, it will give you the most accurate indication of what is actually happening on site, and as a result, it will show you the correct reflection of the power factor and any harmonics associated with that. And this can be done through a number of equipment, power analyzers, or through high-level meters that may be installed at the equipment or the MS main switchboard or at the main distribution board level. It is also good to check the voltage and individual current harmonics as well in these equipment to give you a good indication of what is actually occurring on site. Furthermore, we can go through site, conduct an on-site analysis and review things like having large drives, LED lighting, having heavy starting equipment like DOLs and the like. If there are excessive single-phase loads, the combination of three-phase loads can indicate a sign of unbalanced loading. So these are all good indications that there may be some levels of power quality mitigation that might be necessary on site. But reflecting back on the examples we had discussed, the common theme there is it is always good practice to conduct a power quality audit over a good period of time to ensure that the necessary data is captured and it can be further analyzed to provide an accurate solution for power quality needs. We've ended the presentation a little bit earlier than expected, but I hope we've ticked all the boxes here, and I thank you for your time.
All right. Thank you, Ravi, for that interesting presentation. I found the content very useful, and I hope that all of our listeners did too. So for our audience, if you have any questions for Ravi, please type the questions in the chat box now. So Ravi, I have a few questions here that were sent to us via chat function while you were presenting. The first question is, will power factor and harmonics still be an issue if I have PV arrays installed?
Yes, so having PV arrays or other supply generation can affect the level of power quality that is on site. Typically during installation, you will need to account for those PV arrays, and then you will need to monitor them using different CTs when implementing an SVG or an APF system. So they can be corrected or accounted for both the PV side and the device side.
Excellent. All right. And second question that we have, what are the common issues you've come across with installing SVGs or APFs?
So installing common issues I've come across during installation of static Var generators or active power filters is can range anywhere from the space requirements at a facility in a switch room. It can be environmental condition, so that they might not have sufficient space in the switch room. The environment might be quite dirty. So with these SVGs and APFs, they are advanced technology, so they do require a room which is cleaner or kept quite clean. So accumulation of dust and things like that, even though they have filters, can affect their performance. And then I've noticed cable sizing and existing infrastructure that wasn't sufficient. So the cables might be too small to connect to the SVGs, or the upstream breaker would not have been sufficient in the switchboard. And to upgrade that upstream device, the customer had to install a new section or even replace the switchboard. So these are some common issues that I've come across.
Okay. And the final question that we have is, one of my customers has their lights flickering intermittently. Is this a sign of bad harmonics?
That is a very deep or very involved question. So flicker is a sign of, it could be harmonics and it could not be harmonics. When anybody's experiencing flicker, in most cases, it is a sign of bad LED drivers or bad light fittings. If we want to investigate flicker caused by harmonics, it requires very deep investigation, a full power quality analysis over a good amount of time to actually see what is happening on site. So it's very hard to say from just observation of flicker to say whether it is harmonics or not. So we will always need to investigate further to see
Mhm.
the actual cause of the issue.
Mm. Okay, perfect. So that's all the questions that we have. Ravi, do you have any last words for our viewers?
So yeah, NHP are experts in power quality, and we do offer all the other technologies that's been presented. So if anybody has any questions, they are welcome to get in touch with NHP.
Perfect. All right. Thank you again, Ravi, for taking the time to speak to our members today. And thank you to all those that took the time to join us live. Recordings will be available if you want to rewatch or share with your team. And a calendar of upcoming webinars and events can be found on our website. Please register even if you can't attend, as you will receive a copy of the webinar. Once again, thank you so much, Ravi, and thanks everyone, and enjoy the rest of your day.